So hello everybody, welcome to the second day of the Solidarity Conference. We had a brilliant day yesterday and I'm sure today is going to be as brilliant. This session, the first two talks are going to be given by two applied mathematicians. I'll introduce them because unfortunately the chair of this session, Jouko Vannanen, had a small accident and cannot join us at this moment. So I'm playing Jouko. So let me start telling you about Demetrios Papageorgiou. He is a very international person who comes from Cyprus originally, who has lived in England, in the US, where he was a professor, and he came back to England a few years ago. And he is a professor of applied mathematics at the prestigious Imperial College. He is one of the most well-known applied mathematicians, especially in the subject of fluid dynamics, where he works. And he has very appropriately chosen to talk to us about mathematical modeling, which is what enters into the work of an applied mathematician. He will be speaking on the science and art of mathematical modeling, and in particular, he will be, as you could see from his abstract, telling us about how this notion of mathematical modeling interacts with what happens during the COVID crisis. Demetrios, please.
Thank you very much, Mirna. Thank you for organizing this amazing event as well. So let me share my screen. Where is it? There.
Yes.
Okay. Let me just go into full screen mode and then I think we're good, right?
Yes.
Everyone can see that. Okay, so again, thank you for the invitation. These are the hardest talks to do because you really have to think kind of outside your technical expertise. The technical ones are a bit easier. So I tried to put together oh, sorry, there was something wrong there. Okay, I tried to put together kind of an overview of mathematical modeling and want to explain a little bit what it means to me, how I understand it, and what role it's playing in science, society in general, and especially during this crisis. But as we'll see, there have been crises like this before as well. So what is mathematical modeling and why should we bother? Why should we care? Well, to me, it's a description of phenomena. So we want to describe phenomena using mathematics and using any of the tricks and any of the technical arsenal of mathematics we have at our disposal, because many of these problems are very important, they need to be solved very quickly, as we see with the COVID response. And people have to bring in all sorts of expertise. So this is a truly interdisciplinary type of activity, I would say. I kind of classified them into two types. One is physical phenomena, for example, predicting the weather, astronomy, engineering, health, all sorts of things like this, where we can observe things and make experiments that are repeatable, so that we can describe these with accepted sets of equations or models. And then we also have social and societal type phenomena. For example, describing elections, pandemics. Pandemics kind of sits in between the two, I would say. And kind of way off the scale is probably predicting stock market motions, which may be just a very random type of activity, even though a lot of very good science has gone into that as well. And it has informed other branches of science also. So, so the underlying similarity is that all these phenomena can be cast into mathematical language. And the language we use is really differential equations and partial differential equations. Now, of course, the complexity of models can vary hugely. So, for example, the apple dropping on the head of Professor Newton there is a much less complex, at least now, it's a much less complex phenomenon than a pandemic, which has lots of facets and lots of additional complexity. So model complexity is something we need to worry about and keep in mind. So my personal philosophy for good mathematical modeling practice is to identify a problem that's worth studying. Then we need to formulate some laws, underlying laws, whether these are physical laws or interaction laws and so forth. So once we have those laws, we can translate them into mathematics, into equations, and then we need to reduce complexity. Otherwise, these will be way too big to compute or to get any idea of what the phenomena are, as I will show in an example later. So we need to compute, analyze, in other words, use all the available technology we have in mathematics to get solutions. Also, as far as I'm concerned, we should make everything publicly available for anyone to look at it and be able to reproduce results, because without that, the model loses its trustworthiness. And of course, we have to get the physics correct, get the right methodology. So I'm just going to show a couple, two kind of tangential examples. This is kind of from personal experience. Growing up in the Greek world, you're bombarded with myths from a very early age, and they stay with you. And then, of course, after a while, you discover you discover that people believe there's only one God and not 12. But never mind, we won't go there. This picture, the myth of Daedalus and Icarus, is very interesting to me, because as a child, what we're told in the Greek mythology is that when father and son escaped King Minos's palace, Daedalus was an incredible inventor, so he invented these wings that they could use to escape. And the myth goes that they flew very high up, and Icarus, young Icarus, was going higher than his father, and therefore he was closer to the sun, and the sun melted the wax that was holding the wings together, and he plunged to his death on the island of Icaria, actually, which is named after him, in the Aegean. Now, of course, why do I say get the physics right? Because that explanation is of course wrong, right? Because the higher we go, the lower the temperature becomes, as we can see if we fly in an aeroplane and look at the temperature outside. So that doesn't hold. But I think what the Greeks were trying to tell us there, and it resonates in the current state, is that there was a kind of technological hubris in that if you think you've solved everything and you don't realize that there could be little problems that could happen to topple your edifice, then this can happen. And I think we can see that with this pandemic in the sense that we feel we're at a very advanced stage of our technology. We can do nothing wrong. We'll keep going. But then this virus happens and we're completely upside down. So talking about pandemics, let me go back to the 14th century. And again, this was a much worse pandemic than what we have now, the Black Death. There were 75 to 200 million deaths. So it's about half the Earth's population. It took about 200 years for the population to recover. And again, people were very concerned. And as we did now, they called in the experts. And in particular in France, King Philip VI, he asked the Paris medical faculty to investigate this. So the scholars pored over old texts and they consulted and so forth and came up with an answer. And the answer, it kind of looks ridiculous to us now, but the answer was astrological, in fact. They decided that there was a certain conjunction of the planets and so forth. Now, of course, we know that's not the case, but why do I show this? The main reason I'm showing this is that astrology, the connotations that we have of astrology now were not what was believed so many centuries ago. But to me, the main interest of astrology is that it really is one of the biggest data science experiments or data science collection, if you like, data collection that has taken place. In fact, I was reading a review in the Times Literary Supplement a month or two ago. Apparently, in the last 10,000 years or something, there have been recorded by astrologers over 30 million events. So they actually keep them and they record them. And of course, all this data had a big impact on later research when people were studying planetary motion. So,
excuse me, Demetrios, sorry
yes.
to interrupt you, but I have a feeling that you're moving the slides. Are you? Or are you still showing the title slide?
Oh my God, no. Why is that happening? Sharing is paused. Why is that?
I don't know.
Let me try again. Let me try sharing again. Oh
yes.
My God, sorry.
No, it's just, perhaps you could just show us the few that you already talked about.
Is that showing?
Yeah. Mm-hmm. Now it's showing 3 examples, yes.
Okay, so let me, is this showing now?
The
yes,
Black Death
we have
of 1346.
Okay.
Yes.
Okay. Yeah, sorry, I don't know what happened there. So yeah, what I showed was the myth of Daedalus and Icarus, and that's from the painting from the Prado. And then I talked about the Black Death, and in particular the astrological type of interpretation of this. So we can still see, yeah?
Yes.
Okay, sorry about that. Okay, so let me get into the main part so that at least I can try and finish. I want to give 3 examples, kind of ever increasing complexity, if you like, of mathematical modeling that have been successful over the years. The first one is gravity, and that's classical mechanics, and the story goes back to the ancient Greeks, as many things do, in the physics of Aristotle, the physika in Greek, as we can see on the slide. And Aristotle was an amazing philosopher and scientist. He actually got this one wrong, but it was wrong for several thousands of years before an explanation was given. He believed that the speed of objects depends on their weight. So in other words, a heavier object, if released, will fall at a faster rate than a lighter one. And of course, that's true if you drop a feather and a hammer or something, but that's due to air resistance. It was not until Galileo that this experiment, and we're told anecdotally that he did the experiment from the Leaning Tower of Pisa, where he released two cannonballs of different weights, and they of course landed at the same time. But ingeniously, what Galileo did, and this is not as well known, possibly, as the Pisa experiment, is that he slowed the force of acceleration down in order to be able to observe things. So how do you do this? He put things on an incline. So he put a cannonball that could roll down an inclined plane, and he asked the following question. Suppose I release the ball here, and after 1 unit of time, 1 second, let's say, it travels a distance d. And then I wait 2 seconds, 2 units of time, and measure the distance again from the point of release. And then 3, and then 4, and so on. And the question is, what is the distance? And he came up with this table here, or he actually solved the problem by observation. And he found that the distance is proportional to the square of the time. So in other words, after 2 seconds, it's 4 times the initial distance, and then 9 times, and so on. And in fact, this is Newton's second law of motion, and had to wait a few years to be formulated. And he was so excited about this, Galileo, that he wrote, "Mathematics is the language with which God has written the universe." And now we move on, again, keeping with gravity, move on to Kepler, Johannes Kepler, who was about the same time as Galileo, whose research was purely observational. He would just observe the planets and make detailed data simulation that he then analyzed and came up with these, amazingly came up with these 3 laws. Three of planetary motion. One is that the orbits are ellipses. They're always ellipses, and in our solar system, they're around the sun. Then, in equal amounts of time, if a planet travels an equal amount of time, 6 months, let's say here, or 6 months in a different position, then the area swept out between the sun and the planet's position is the same. So the areas are equal in equal time. And then even more amazingly, he found that the period that it takes for a planet to go around the sun is actually proportional to the half major axis of the ellipse to the power 3/2. So this may be too much to take in, but it's just amazing that he managed to do all this. So just by observations. And then the question is, can we build a mathematical model to predict all these things? And this is where Issac Newton comes in with a law of gravitation, a universal law of gravitation, which is very, very simple to explain, but whose effect explains the motion of planets in this idealized mathematical model. So the law is the following. It says that if I have 2 masses, mass M1, a smaller one, and a bigger one, so think of it as 2 planets, then they have a mutual attractive force between them. Let's call this Fg, this force, right? But then what the law says is that if you now double the distance, so the distance between them is r there, if I double it to 2 times r, then the force, the attractive force goes down by a factor of 4. So in other words, the force is inversely proportional to the square of the radius. And simply using this gravitational law, and this is what I meant before by mathematical models needing laws, simply using this law and 3 other laws that Newton had that we teach in high school even nowadays, F equals ma, force equals mass times acceleration is the basis of lots and lots of things. He was able to really explain mathematically all the laws of Kepler, and along the way he had to discover calculus and so forth. So this is so advanced now that we actually teach this in first term applied mathematics courses. Now here's a more modern application of this. and that's to do with interplanetary travel. What you do with interplanetary travel, you don't have huge amounts of fuel on board that propel you from one place to the other. What you do is you hitch rides on trajectories, gravitational trajectories of different planets. So here's a simple cartoon that tells us how something that's in orbit then gets pushed around the Earth, gets pushed out of orbit so that it gets into an orbit around the sun, but then it gets pushed out of that again with propulsion systems to then get attracted into the region of another planet where it needs to arrive to. And this can all be worked out by Newton's laws of gravitation. And indeed it is. This is a document from the Federal Aviation Authority of the US. Okay, now let me move to my second example, epidemiological models and COVID-19, and consider the topical questions that we have now. And the aim is really to describe the spread of a disease so that we know how to respond to it. This is just one aspect, of course, of fighting these diseases. The models used now are very complex, but they're essentially based on what's called an SIR model. And that's what I want to try and explain a little bit. They're compartmental models. And these go back to about 100 years ago. This was a paper by two medics, in fact, from Edinburgh, Kermack and McKendrick. And this is in the Proceedings of the Royal Society. It's a very nice read if anyone is interested in this type of thing. What this simple model is, it splits a population of size n people in a population, into three compartments. And these three compartments are the susceptible people, so the ones that can catch the disease, the infected people, the ones that already have the disease and therefore can infect people, and then the recovered people. And the assumption here is that once you've passed the disease and you're recovered, you're no longer susceptible. So the idea is to model this and try and see whether everyone gets recovered or everyone dies or everyone becomes infectious and so forth. So these are simple models, and this is how they feed. Susceptible people feed into the infectious through a rate that depends on this parameter beta and their respective numbers. So S is the number of susceptible, I infectious. This number beta is really this R0 parameter that we've been hearing about in the news a lot, which is something we don't know, but I'll say something about this coming up. And then, so susceptible feed into infectious, and then infectious people lose people when they're recovered, right? Through a certain rate, gamma times I. So that's a proportion of the population of infectious people become recovered. And then we can put the mathematical model, simple differential equations in this. So ds dt, so the rate of change of the susceptible people, it's going to decrease as they get infected, okay, according to this rate that we introduced earlier. Now, of course, the rate of the infectious people will increase exactly by that rate, but also decrease by how many people recover or die. And then, of course, dr dt will increase by how many people who were infected recover. So, sorry. So so this parameter beta, as we said before, it's got built into it the probability of disease transmission, as well as the number of contacts, average number of contacts of individuals. So it's exactly this R0 parameter. And gamma is the rate at which infected people recover. Okay, so there's been, as we know, a huge international effort in doing this. Lots of groups sharing results and data. I'm very, very aware of our own effort at Imperial, and there's a link there if anyone's interested, with a very, very kind of general description of what their activities are. And of course, all the papers are available there too. So a huge international effort. The model I showed before is the basis, but it's way, way too simplistic. So this has been added to by taking into account the characteristics of the population in different parts of the country or different demographics and so forth. So the compartments get compartmentalized even more. And of course, a lot of this is data driven. We need to know data about these various groups in order to model them. As I said before, this familiar number R0 is related to beta. And of course, mathematically, that previous model, if I knew beta and gamma, that's a very simple thing to solve. There's nothing to do. The problem is that we don't know those rates, and we have to use models and fitting of parameters from data and work backwards as well in order to get them. So there's a lot of inverse problem methodology going on there, as well as data training algorithms and deep learning. So these are simply complex data acquisition methods, if you like, from all the data that's around. So the more data there is, the better informed the models will be. Now, the transmission rate, so it's all built into this beta. The transmission rate, of course, depends on lots of other things. And my big interest is fluid dynamics, as Mirna mentioned. And in particular, it will depend on the fluid dynamics of the sneeze. And that's how these pathogens are transmitted. So let's go there first. So what I want to do is the last example is to go to continuous media. So what we've shown up to now is planets moving where I assume they're points, and there's a law between them, and I get n-body problems, or two planets, or 3 or 4, and so forth. So what happens if I have continuous media, like liquids, gases, elastic solids, and so forth? So let's do I'll do a very naive calculation to show that we need to think differently if we want to solve problems like this. And the naive calculation will be based on exactly this particle-based model that I used for planets. So I had 2 planets. There was a law of an attraction force. So if I have a cup of coffee with whatever, 300 milliliters of coffee or something in it, then I can think of describing the molecular interactions in this liquid through some law to describe the motion. And if I have 2 molecules, I can write down an interaction law. So that's known, and I can write it down. But then I have to interact all the molecules together. So the big question is, how many molecules are there? Well, this follows from Avogadro's number. It doesn't matter, these are details, they can be worked out. But there are roughly 10 to the 25 molecules in a cup of coffee. So if I were to interact these and ask the question, how long will this take on a 2 gigahertz processor that does an operation in 10 to the minus 9 seconds, and think of just one operation as one interaction between 2 molecules, then we get this astounding number. The answer is 10 to the 33 years. So we can see that this is nigh impossible, especially to put it into perspective. The life of the universe is 10 to the 7 years. So we need to do something much, much more different. And this is where the breakthroughs happened about 200 years ago or so. And that's in the 19th century. That's the Continuum Hypothesis, which says the following. If you have a continuous medium and you assign to every point in space, you assign a density, a velocity, a pressure, or whatever else physical variables you have. And then this gives a continuum description. So you think of it as a continuous function in space. Then we apply Newton's laws of motion, but to arbitrary volumes of the material, not particles. And each volume will have lots of millions of these molecules in it. Once we do that, we can derive mathematical models. I'm just showing this just to show some mathematical symbols. Don't expect this to mean anything to many people except Jean-Marc. So this is the Navier-Stokes equations for fluid motion. So what's interesting is that we went from discrete to continuum, but now we have to go discrete again to solve this numerically, because there are no solutions, or no general solutions of this equation. In fact, existence of solutions is one of the Clay millennium problems for this system of equations. So I need to discretize again. And this is the type of thing we need to think about in modeling droplet ejection from a sneeze, let's say. So this is a beautiful picture, some amazing experiments by Lydia Buruiba at MIT. She's got a great web page as well with lots of movies of the various experiments she does. And recently she found that violent sneezes can have as much as 7 to 8 meters reach. And the reasons are because it's a hot fluid and it can transport things further without them evaporating. But these are details. So the question is, as far as about the safe social distancing rule, what should it be, 1 meter, 2 meters? It's fairly arbitrary. So the answer is we don't know. And there are examples where they say it should be 8 meters. So what can we do? So what I want to show, and then I'll stop, is really to show how I can use these equations, use this mathematical model to really get into the fine details of things like a sneeze and droplet fragmentation. So what I'm going to show you is simulations of drops which are falling onto a surface, just a flat surface, so they're going to splash. So we're going to go from small drops, about 20 microns, to larger drops, 200, 2000. To give you an idea, the diameter of a human hair sits somewhere in between these two. Okay, so these are tiny droplets, huge applications, by the way, in all sorts of things, not just COVID. So let me show a couple of movies, which hopefully, can you see this? I hope you can see it. So let me show a couple of movies. So these are computer simulations. So these are in silico experiments. So a droplet falls onto the plate. It's small enough that it then retracts back.
I think you need to change the screen, Demetrios.
Oh,
because we just see the slides.
Sorry, how do I do that?
Well, you stop the sharing and then you go to sharing and choose the screen where the movie is.
Okay. Okay, I know how to do that then now.
Okay.
So here it is again. So this is the small droplet hitting the flat plate. It's small enough that it gets retracted back. So something this small will not cause a spray, if you like. Of course, there's no flowing air over it and so forth. Let me go back and do this one now. And I'll do the sharing again. So this is the medium-sized droplet. So we can see there's more deformation, but then once it hits, it generates all these tiny droplets. But by the way, I should say that the whole time span of this, if you put it in real physical variables, it's microseconds. It's really way too fast for cameras to catch, and they fragment very quickly as well. And then finally, let's do the large drop. This is the last simulation. This is the large drop, and we can see even breakup way before it hits the ground, and this huge amount of fragmentation. Now, what we can do with computers is that we can actually go in and interrogate every one of these single droplets so that we know how much will fly off. So this is exactly the kind of thing that we have done. So let me share. Go back to my presentation. So we've actually did a lot of data acquisition from all these things in order to solve problems in the aerospace industry. Actually, we didn't do this because of COVID. It was a related problem where we want to see how much ice forms inside jet engines, because it can be very dangerous due to droplets impacting. Okay, so I've finished. So what I'll do, I think I went over and I apologize about that. What I'll do, I'll just leave a bunch of conclusions or points for discussion randomly chosen. And the second one is for Mirna to decipher.
I know it's Archimedes, but I can read. But
Yes.
what does it say before that? Dos my read, please.
Pastukaitan gar. Kineso, yeah.
Kineso is movement. Something
So
with
if I say
movement.
it in the Greek accent, is dos mi pasto ketangan kiniso. It says, so what it says, kiniso we can recognize is like kinetic, right? Yi, gan, this is Jaya, this is the earth. So in fact, what Archimedes is saying there is, give me a place to stand and I can move the earth.
Well, yeah, we all learned that one, but not in the original.
So this is the technological hubris we were talking about before. And that was because he was very excited about this method he discovered for levers, and he built levers as well. In fact, Archimedes essentially discovered calculus in a sense with his the method of exhaustion, it was called. Anyway, I'll stop there. I can just carry on talking forever, but my main point is that mathematical modeling is useful, but it's part of a bigger enterprise. Definitely interdisciplinary, and interdisciplinarity is getting more and more important as we move on. Lots of new tools that we can use, including artificial intelligence, biotechnology, and so forth. Computing, we don't know. Quantum computing hasn't taken off. If it ever does, we don't know. But then philosophically, my idea is we should get more scientists to work on big problems and important problems like climate change and energy, sustainability, health, and so forth. And here I can just say one thing, which is it's a kind of a good omen. In the last 3 of my PhD students that graduated in the last 2 years have all gone into energy sustainability postdocs, and they're working on batteries. And 10 years ago, they all went into banking. So I think we're on a good positive trajectory there. And of course, science, I don't believe science can solve climate change so that we carry on behaving as we are behaving now. I think what science can do is help society change so as to preserve the world. Otherwise, everything will get thermal runaway and it's over. And finally, I think artists, philosophers, scientists, we have a big role in society, and we need to be promoting knowledge, truth, and honesty in everything we do. So I think I'll stop there. Thank you, Mirna.
Thank you very much, Demetrios, for your excellent talk. I agree with every word you said, except with the definition of the continuum hypothesis, which instead really means something entirely different.
Yeah, in fact, I can tell you something interesting there because of that, because I used to teach a class at Imperial on continuum mechanics, things like this. And then the first class I emailed the cohort saying that I was going to discuss the continuum hypothesis. And I had 250 students there, and they were kind of some of the pure students as well. So now I know it's a different thing, yes.
Yes, but to pass from the inner jokes to some more serious questions, Gisela has asked me a question. She asked this question in French because it's complicated and she prefers that I translate it for her. I think it's a very good question, which she asked looking at the fact that this modelization actually was given, this SIR modelization that you explained was given in 1927. She supposes that this was because of the Spanish flu. That is, I don't know if this is the case or not, but it seems that it could have been. Is that true? Yes. So she says this means that if we count that we have collected the data by 1920, it took 7 years to make this equation. Do you think that in this particular epidemic that we are living, it will take us such a long time? We would hope that it will take us less time, and if we do, why are we confident it will take us less time? It seems urgent that we, model quickly.
Yes, yeah. No, I think that's an excellent question, and I think two aspects to this that I can contribute. One is that with this pandemic, at least what I'm seeing with all my scientist friends around me, is that this is kind of a bit like a Sputnik moment. Everyone has dropped lots of things, and they're just working on this in all sorts of different areas of science. Mathematicians, I know lots of mathematicians who are doing these things. There's a big initiative in the UK, in Europe, where people come together and they're given questions, and then they use their collective expertise to try and answer them. In fact, there's a workshop on the 29th of June that's happening that I'm going to. And on a happy note, I got an email late last night from a friend from Cambridge who's been working on these models, and he was very excited. He did some new data analysis and things like this, and he believes that that the virus is getting weaker. Again, this is all through using these data analytic things, but coupled with technology we didn't have in 1927, and that's computers that can interrogate the data in all sorts of different ways. So I'm optimistic. I'm optimistic about us finding the path of the virus. I'm sure a vaccine will follow, and again, again, talking about computational tools and artificial intelligence, I mean, this part, artificial intelligence, will play a vital role in designing future drugs, because you don't have to do them in wet labs. You can do them all on computers now. But of course, that's a big stretch, right? Out of every 5,000 possible drugs, only 5 make it to trials, and out of those, only 1 makes it to approval. So there's a huge benefit to be reaped from things like that. So on an optimistic note, I think we will get through this. What needs to happen in a much more serious way is the response of governments and politicians, or at least we have to be ready for things like this. Sorry for the long-winded answer.
No, that's fine. Gisèle, t'es contente? Ton micro ne marche pas.
Oui, on n'entend pas, Gisèle. Non, ça marche pas.
Maybe I'll stop sharing so that I can see everyone.
Okay. I think Gisèle is trying to turn on the microphone. There are some problems. Here is Menahem.
Maybe I can
Menahem,
make
are you trying something? Yes, please, go ahead.
a remark more than a question. You said, of course, a great optimism in the role of science to help solve these major problems, epidemics or other problems. Now, one thing that I faced is trying to propagate this idea of science and using the scientific infrastructure worldwide to try and deal with the problems, is the fact that there is a certain overconfidence of the scientist. We kind of, at least convey, or some of us convey the impression that we can solve it very quickly, that we'll have definite answers, we know exactly where the virus is coming from and how it spreads and so on. And now actually we are facing a kind of crisis of beliefs, because we don't have the answers. We don't have a very clear answers that we can confidently claim to be the answers. And therefore, politicians, public opinion is now very suspicious in a way of scientific, and that actually encourages all kind of pseudoscience. And it's a very tough job on the one hand to propagate the use of science to solving the problems of society, but on the other hand, not to give the impression that we have the solutions right away. We have somehow to keep insisting that the process of science is long, it's not straightforward, you don't always get the answers right away, and I think it's important to keep a certain level of modesty.
Yes, I completely agree. Thank you for pointing this out. And this is exactly what I meant by the technological hubris that I flashed on the screen. In fact, there was very interesting. There was a book very recently by Stephen Kotler, who is he's like a business management person with Peter Diamandis, and the book is called, let me see, it's called The Future is Faster Than You Think. And this book came out during the pandemic. And what the thesis of this book is that there's this brave new world where everything will be solved. We'll put little robots inside our bloodstream and everything will be monitored, and longevity, there will be an escape to longevity and so forth. So I couldn't agree more. Science is fundamental, and a lot of these problems we're trying to address we don't even know the underlying equations, right? We don't even have equations to solve. So it's all a big patchwork of things. And politicians, of course, want answers yesterday. And in fact, I don't think many politicians understand what exponential growth means. You know, if you ask,
I couldn't agree more, but I think it's also our fault because we have let politicians run our life, and we have let them decide about the funding. We have let them treat us as some sort of disposable objects that they can dispose one scientist by the next scientist that they think they can import from some other country. And we just let them think that it's them who run the show. I have another question, which will be the last one, as we are a little bit over the time. The last question will be asked by Maria Clara Cortez. Yes, Maria, can you please?
Yeah, thank you for your talk, Demetrios. It's not so much a question, but I think it's more like I want to point out that there are two theories about the starting of the coronavirus. One of them is this connection with animals, with this closeness that human beings are having with animals. And the other one is the creation of the virus in a lab. So there are these two different paths that actually point out to what Menahem was saying about science and what you were saying about science, and how far science takes us from natural things. You know, how science becomes in a way dangerous because it creates this faraway connection with nature, and it actually, you lose the contact with what actually may happen in nature. So, and one of the theories that why we are the way we are now is because human beings are connecting with nature through microscopes and all kinds of images created by tools, but they don't actually touch reality. So I think we are, this is like a fight of two different ways of facing the problem. And I ask myself, well, yes, science can help us a lot, but I think it also take us far from the problems. So it's just, I don't know.
yeah.
No, thank you for a comment, Demetrios.
That's a very, very interesting comment. In fact, science can go completely wrong as well. I mean, one example I can give is the stealth bomber that the US Air Force built. It cost 50 billion, I think, and they built about 20 airplanes that were never used. So, you know, that's a lot of money wasted because they felt they could do it. Well, there was the Cold War going on and things. But yes, science is not always the answer, or the use of science has to be done in a very careful way, for sure.
Indeed. Well,
Thank you.
I think that we'll stop here. Thank you very much, Demetrios. It was an excellent talk, which made many interesting reflections.
Thank you.
Yeah, I suggest just that we go straight into our next talk, which will be